Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen. As usual, I would start from the summary of the previous lecture. I know you are very busy and you have forgotten something about the previous lecture, but I am here to help you. No need to worry about this. So I am going to start the summary from the previous lecture, that is the correlation. Correlation is simply an association between the variables. And this degree of association is measured by the coefficient of correlation, to whom which we show by the symbol R. So talking about the correlation, one basic property of the correlation is that its range is between -1 to 1. What this means, you know, I discussed it in detail, that if it is -1, it means the relationship, the correlation between the variable is exactly negative. What this means, if one variable increases, the other decreases. If the correlation is 0, it means there is no association between the variable, and if the correlation is +1, it simply means that the variables are correlated, strongly correlated, and their correlation is up to 1. As the variable 1 increases, the other decreases. The second property of the correlation was that it is asymmetric. This is very important, that asymmetric means that the correlation of x with y is equal to correlation of y with x. So it is symmetrical in nature. The arrangement of the variable doesn't matter. The next one characteristic of the correlation was that it is independent of the scale and origin. What this means, if we add or subtract or multiply or divide any of the series and then take the correlation again between the two series, then there is no effect on the measure of correlation, that is the coefficient of correlation. Then we talked about, if you remember, about the causation and correlation. Most of the students of most of the time are confused that there is no difference between the causation and the correlation, but there is a huge difference between the correlation and the causation, because correlation doesn't mean that the variable are causing each other or one variable is causing the other. But in causation, we say that whether x is causing y or whether x is causing y or y is causing x. And how we come to know this? We come to know this from some theory. It may be from any discipline, starting from the psychology to economics. Then we started a very, very broad topic, that was the regression. In regression, there was an old concept in which we studies the Galton law, that states that if there is abnormality in the population, over time, over generation and generation, it converges towards the normality. As I exemplified from the heights of the tall parents and the small parents, and then I showed that their children height converges towards the population average height. Then we came to know about the modern concept of regression. The modern concept of regression is very broad, and in this we are interested in estimating the expected value of dependent variable y on the basis of fixed values of the x. Today we will continue this discussion, and let me start that what we are going to cover today. First of all, as I am sure, I remember I just gave a glimpse of the population regression function. We will continue the story from the previous one, and we will be talking about that what is the population regression function. Then we will talk about the sample regression function, OLS estimate. OLS means ordinary least square estimates. And at the end of the lecture, we will be talking about the assumptions of classical linear regression model, and we may derive, and surely we will be deriving, the ordinary least square estimates. So what is the population regression function? Population regression function, if you see on the slide, that the population regression function is, here look at, that the expected value of the population mean is dependent on many of the regressor, that are the xi. and this is called the population regression function. If you see here, this PRF is called the population regression function. Population regression function. And CEF, as I told previously, that the population regression, in population, the expected value of the dependent variable is based on the conditional expectation. As I remember that what was, I told you that what is the conditional mean and what is the unconditional mean. I would like to here repeat these two terms because we will using it extensively in our discussion. What is the unconditional mean or only the mean? This is the total average of the sum of the population. But it doesn't portrays the true picture. For example, if I say that I am interested in finding the average score of Shahid Afridi, it will give me only that Shahid Afridi has been scoring about 30 runs per inning and this is his average. But if I am interested to know about that what is the average of Shahid Afridi against each country, then now I am going towards the conditional mean, that is against India, Sri Lanka, West Indies and many other countries. So when I will be bifurcating, I will be fixing this average on some of the country, then this will be conditional mean. So population regression function goes through the conditional mean. This CEF means conditional expectation function. Conditional expectation function, as I told here, that this is the story behind this. And now if I replace the excise, that is the, you can see here, that is the independent variable. So I replace with the sum of the other function. So it is based on the beta 1, that is the parameter, and it is also based on the beta 2, that is the parameter. So we are more interested, our total interest in regression is to find the values of the parameter, because if you look at here, if you have the values of the dependent and the independent variable through different method, as we will be talking about the ordinary least square method, you will be getting the values of beta 1 and beta 2, that are the parameters. When you will get the values of the parameters, immediately you will be able to find the expected value of the mean. So beta 1 and beta 2 are unknown. These are the parameters, and what is the definition of the parameter? They are unknown, but their values are fixed, and these are also called the regression coefficient. So this is an alternative terminology, so you should not be confusing about this. If I say that beta 1 and beta 2 are the parameters, then that is the same thing. And if I say that these are the regression coefficient, then there is no difference between the current talking and the previous one. And beta 1 and beta 2 also known as intercept and slope coefficients. So although these are both the parameters, these are the regression coefficient, but they are a bit different from each other. For example, if you see with beta 1 there is no independent variable, but with beta 2 there is independent variable. I would like to show you this from, if you see here that what is the intercept and what is this. Look at here, this is the x and this is the y. If this is the regression line and I say that this is the expected value of y equal to beta 1 plus beta 2x. So from, this is the origin, from here to here, this is beta 1. This is called the intercept. And what is beta 2? Beta 2 is called the slope coefficient. Slope coefficient. Both are regression coefficient, but beta 2 is called the slope coefficient in two variable regression, and here this beta 1 is called, this is the intercept. And what is the slope coefficient? Beta 2 measures the change in the dependent variable with respect to the independent variable. So if I want to see the slope of at this point and this point, this is point A and this is point B, I will simply come here and I will connect it with this one. This is delta y change and this is delta x because it is on the x-axis, and this is on the vertical axis. So these two coefficients, we will be talking a lot about these coefficients beta 1 and beta 2, but that's why I am making you much clear about this beta 1 and beta 2. So first, beta 1 is the intercept and beta 2 is the slope coefficient. And other names, so as we are in the beginning and we are just setting the stage for a huge discussion of regression, we are making clear ourselves about the different concepts, because I will be using these concepts alternatively, so if there should be no confusing that these are the similar terms. For example, if I say the regression, this function is also called the regression function, this is also called the regression equation, it is also called the regression model. The purpose of the regression, now we are inching towards, not we are rapidly going towards, but I am saying we are inching towards the estimation that is our ultimate objective in the regression analysis, to find the values of the beta 1 and beta 2 that are the intercept and the slope coefficients when we restrict ourselves to the bivariate or two variable regression analysis. Next, going towards, if you see, then we will see that if we will be talking about the linearity, what it is, because if you see that our this expected value of y given xi, now it is a function of xi. So we should know about that how the xi variable is generated, because if I simply write it that yi, it is based on beta 1 plus beta 2 x plus ui. I will be talking about that. Now I have made this function as a stochastic or random function. If you see that the yi here, yi is depending on two things, that is, these are the variables xi and ui and the parameters beta 1 and beta 2. If we are interested about the behavior of the dependent variable, definitely we should know about the independent variable, that how they are generated. So first of all, the first thing we will be assuming about this, that the model is linear. I will be talking about this assumption at later stage, but still I have to make clear that what is the linearity. Linearity is a very simple concept, that if the index means the power simply, you know, this is, for example, this is x power 3, this is the index, or you can say this is the 3. So if the index of the parameter should be only and only 1, not -1, not 0, not something else than the 1. It should be exactly 1. If it is 0.5, we will say that it is not the linear. So what linearity means, that the index of the parameter. Why I am using the word parameter? Because we are now talking about two kinds of linearity. First is linearity in parameter. This is first linearity in parameters, and you know what are the parameter beta 1 and beta 2. And what is the second? Linearity in variables. So it means if we are interested in the linearity of the parameters, we are saying that the index or the power of the parameter should be only 1, nothing else than 1. And if we are talking about the linearity of the variable, then we will be talking about the index or the power of the variable should be only and only 1. So again, going back, if you look at this model from here, you will come to know that this model is linear explanation. beta 1 and beta 2 and x. If you look at the independent variables and right hand side, there are parameters as well as the independent variable. You will come to know the power of the beta 1 and beta 2, that are the parameters, their power is 1. So it means this model is linear in parameter. And interestingly, the power of the x, if you look at here, the power of the x is also 1. So very interestingly, this model is not only linear in parameter, but this model is also linear in variable. Come to the next model. If you look at here, these things are equal, but if you look at the xi, this has now become in square. So what this means, the power of the variable is now not 1. So I think you have guessed that this model is linear in parameter, but it is non-linear in the variable. So this was we talked about the linearity of the variable, and now if we say the linearity of the parameter, the similar things here, beta 1 and beta 2 has the only value of power of 1, and here you can also see that although the model has become nonlinear in variable, but it is still linear in the parameter. So what we will be talking about, whether we are interested in linearity of the parameter or we are interested in linearity of the variable. In our throughout regression analysis, we are only concerned about the linearity of the parameters. We have nothing to do whether the variables are linear or non-linear. If they are linear, then good. If they are non-linear variables, then there is no matter. But we are taking the very fundamental and the basic assumption about the parameters, that are your slope coefficients beta 1 and beta 2, that the model should be linear in parameter. I would like to show some slopes and some curve that are showing the models that are non-linear in the variable. So I will be making some of the graphs. So I am going to show the shape of the function that when they are non-linear in the variables. So if I would like to say that, look at this. This is the x and this is the y, and I am first making that the function is linear in the parameter as well as linear in the variable. So this is the line, and it is y is equal to beta 1 plus beta 2 x. This model is, this function, this line is not only linear in parameter, but this is in linear in also variable. If I say that my function becomes of this kind, this is x, this is y, and I say that this is now the function. I am sure you have guessed that this is the non-linear function in the variable. So what is this? This is in the quadratic form. This is quadratic form, and I am sure you know what is the quadratic. Y is equal to beta 1 plus beta 2 x plus beta 3 x square. Now if you see clearly, beta 1, beta 2 and beta 3, that are the coefficients. That are the coefficients are the parameter. The model is linear because the index and the power of these betas is equal to 1. But if you look at now here, you will see that this power has become non-linear. This is the power of the variable. Now what this means, this on the right hand side, the function is non-linear, and this is non-linear in the variable. If I make such kind of model, again taking x on here and y here, if I make such kind of model, this becomes cubic model. In mathematics, these are some of the mathematic concepts. Look at here, in this way the model is y is equal to beta 1 plus beta 2 x plus beta 3 x square plus beta 4 x cube. So this is the cubic function. What to show this? Not to show the mathematics, but to show that you can see that this model is again linear in the parameter, but this model is non-linear now in the variable. Why? The index of the variable x is here 3 and here is 2. One more example I would like to show you, that this is x, this is y, and this is the exponential function. Here the y is equal to e power beta 1 plus beta 2 x. So again you can see that this model is linear in the parameter. So after this linearity concept, I am going to introduce the stochastic or the error term into the, you can say, the population regression function, and I will show shortly that the expected value of this error term is equal to 0. This is our assumption. So introduction of the random term into the model, if you look at this, our model is, for example, I would like to write here that this is the model y is equal to expected value of y given xi. When we take the expected value of y, this means now it has become a constant, and this is mean. And because this is the value of this y given on the xi plus ui, now this is ui, this is the stochastic term, this is the error term, this is the residual term, this is the error term. So what this means, now the relationship is not exact, and now there is some margin of disturbance. If I further explain go for that y is equal to, simply I am replacing expected value of y over xi, and it is beta 1 plus beta 2 xi plus ui. If I apply the expectation on this function, this will become, this is yi, this is also yi. If I apply the expectation, now definitely it is a mathematical concept, I am sure you will be you have knowledge of basic expectation approach. If I apply the expectation on both terms of the above equation, it will become yi, and if I apply the conditional expectation, it will become yi given xi. If I only apply the expectation, that I will call this is the expectation, but I have applied the conditional expectation. And now it is expectation of, this is y, this is expected value of y given xi. I am writing this equation here, y plus expected value of ui given xi. So what this means, it will become expected value of yi given xi on the left hand side, and as I said that the expectation of a constant. Now this is the constant. Now this is the constant, because it is, we have applied the expectation already in the bracket, and when the expectation or the conditional expectation of any of the constant is always equal to the same constant or the constant itself. So it will be equal to, now this is the constant, expected value of y given xi plus expected value of ui given xi. So what is this? Interestingly, now these two terms are the same, because when we fix the xi, then there is no difference between this. If we do not fix the xi, then there is difference, but when we have fixed this, both are the constant and now they are the mean, and simply ui is equal to expected value of yi over xi minus expected value of y over xi, and as I said, these are the same term. So expected value, this is the expected value of ui given xi. So what is expected value of ui given xi is equal to 0. So what this means, that now I have introduced the concept of stochastic or the error term into the population regression function. In population regression function, we are interested in estimating, predicting, or finding the expected value of the dependent variable on the basis of the x variable that are the independent and they are fixed. So as we solved this equation, we came to know that in population regression function, the expected value of ui given xi is equal to 0. I will be explaining when we will be talking about the assumption of the OLS. I will be talking about same thing, and I will be showing you this diagrammatically. Sample regression function, just a jump from one regime to another regime, from one area to another. Because why are we going towards sample regression function? I think need not to tell you that we cannot estimate the population regression function, and you have number of reasons behind this, that it is impossible to study the whole population. So what we do, as we are unable to study the whole population, we try to see the behavior of the population regression function on the basis of sample regression function. So what is the sample regression function? Task is to estimate the population regression function on the basis of sample regression function. This is our task. Now only one value of y against xi. This is very important. If you see here, if you remember my previous example, here was the income, weekly income, and here was the expenditure. And what was this? For example, here a families are 80 income per week, and they have consumption, for example, 50, 60, 70, 80. So in the bin of 80, in the area of $80 or 80 rupees income of a family, there are four families who has the consumption 50, 60, 70, and 80. And similarly, let me give one more, and I think there is another group who has weekly income of $100, and there are 6 families. For example, this is, you can say 70, this is 75, 80, 90, 95. So these are 6 families. What is the difference between the population and the sample? In sample, we will be just taking one value of independent variable against the one value of the yi. So one matching of one value of y with the one value of the x. So what we will be doing? We will be taking only one value, as we are, for example, if I take the sample, I randomly select this, and from this bin I randomly select, for example, this. So now you can see that out of many of the families that have the consumption of different values, in sampling I chosen only one from first bin and the second from the second bin. So instead of all the values as in the population, we are sampling now, and we are taking one value of x against the one value of the y. And it is very interesting and worth $1 million question, that can we accurately estimate the population regression function from the sample regression function? Yes, although we cannot exactly and 100% accurately measure this, but there are techniques that help us to see that our estimation is very, very near towards the population estimation. In other words, I can say the sample regression line is very, very likely to like the population regression line or the function. Fluctuation in the sample. This is very interesting because many people will be taking the sample. For example, if a person take this 60 and this is the other and 95, the other when sampling randomly select this one and I say this one. So it means there are now 2 samples. So what this means, there is fluctuation in the sample. One person sample is different from another person sample. So what this means, as there are many sample, as there are sample regression line. because everyone will be estimating his regression line, and when we have accepted that there are more than one sample, so every time every person will come up with a new regression line. What this means that if there are n samples, n people take the sample, there will be n regression line. For example, this is first regression line. I will say this is sample regression function 1, this is the other sample regression function 2. I am just supposing that there are 2%, there are only 2 samples, and these are the regression line. Which line is more appropriate? This is very interesting question, and simply speaking, the line that is more representative of the population regression function, that is the best line. And how we will come to know that which is there any intuition? No, there are mathematical solutions, there are mathematical measures, there are statistical measures that help us in finding that which regression line is more near to the population regression function. And simply the best is which is close to the population regression function, or in other words you can say the sample parameters should be as close to population parameters as possible. That beta 1 that you estimate, these should be very, very close to the original, or you can say the population regression parameters. Now I will be introducing the sample terminology. In regression we do not use the words hat. We will be using here, if you look at here, this function, you will see the first is yi hat. Hat mean now it is estimated. You can call it yi hat or you can call it yi cap. No restriction on you. It is up to your discretion. Now what this means, this is beta 1 hat. What this means, now we have, using some statistical and mathematical technique, we have found the numerical value of the beta 1. Now it is not unknown, but we have found its value. And we will be talking about that how we find their values. So you will come to know that as we will be deriving the OLS estimator, I am sure you will be learning from this. Look at here, the similar thing is with this. Now this is called beta 2 hat. It is also estimated, and you know this is the slope coefficient. Here you can see that the y hat is read as y hat or y cap, and yi hat is estimator of expected value of y given x. So if I take yi hat, it means it is a parallel of expected value of y given xi. So now this yi hat is a value in comparison with the expected value of y given xi. And similarly here you look at this, now this is beta 1 hat is a now representative of beta 1. Beta 1 population parameter and beta 1 hat, now you have estimated this, and this is from the sample. Beta 2 hat, similarly beta 2 hat is now representative of beta 2. Now the population regression function can be divided into two parts. Again coming back to population regression function, if you look at this, this is y hat, any of the y value, and what is this? This is beta 1 hat plus beta 2 hat xi plus ui. What this means? This area is explained area. You have estimated the value. I will call it that this is the explained. Y is something. Out of y, this area that I have underlined, this is explained. Explained. And this ui is unexplained. And unexplained. For example, if yi is equal to 70 plus 10, so what this means, 70, if it was 80, so 80% of this, out of 80, 70 was explained and 10%, or you can say, is not explained, and it is in the error term. In this we have included the ui, that is the residual term. Now the final form, I am thinking that you may be mixing up the ideas, so I have come up with the final form of the population regression function and the sample regression function. So what is this? If you look at this, that I have highlighted this, that yi is equal to beta 1 plus beta 2 xi plus ui. Simply there is no hat over this because these cannot be estimated. So if there is no hat over this, hat means these have been estimated, cap means these have been estimated, and against that simply the model is in sample regression function. This is yi, it is equal to beta 1 hat plus beta 2 hat xi plus ui hat. Now you can see that we have estimated all the values. Now I would like to combine this. Now these are beta 1 hat is representative of this, beta 2 hat is representative of this, and these are representative of each other. So if I would like to show you this all story on the diagram, I am sure it is very interesting and it will help you that which is unexplained and which is explained. So I would like to draw this on the diagram. The diagram is also there, but I would like to draw it separately. So this is x, this is y. I suppose that this is the population regression function and it is equal to beta 1 plus beta 2 x, and y is equal to this one, yi is equal to xi. So but I think I say that someone estimated this line taking the sample and his regression line was of this kind. So what is now? This is equal to yi hat is equal to beta 1 hat plus beta 2 hat xi. And now I further suppose that this is the xi. This value is xi, and I go over this xi to the up. I connect this to the population regression function and I take further it above here and I further it take away from here. I suppose now I have to increase it also. So this is, suppose there was a one value that was the yi. This was our original or the observed y. So what this out of this yi, this is, you can say, this is on the population regression function, so this is expected value of y given xi. So if I draw this to this side, again I can write the same thing here, that this is the expected value of y given xi. Now if you look at here, out of this y, we have estimated this. So this is yi hat. This is yi hat. So what this means, look at here, the value was yi. I will be giving the number to these. First try to understand from here to here up to this point, and this is the ui, unexplained. What this means, that the yi was a value and we estimated this. We estimated this portion of the yi from here to here, xi to from here. We found this portion, but from this point to this point, that was ui, that was the unexplained. Now this was related to the population regression function. Now just take it up. This is similarly, I am just showing the same thing on here, yi hat, and I can also show this on here, yi. So what this means, now what we estimated out of this yi, from here yi to from here xi, we have estimated up to here. From yi hat to here, we found this value out of this, but if you see from here to here, now this is ui hat. Now because we have now estimated and I have taken it on the dotted lines, so this is now ui hat that we could not, that was not explained. I would like to give you the number. For example, I say coming on this side, I say that the yi value was 100. Suppose, I am supposing. And what this, the population mean was, this was the 50, and we estimated it as 70. So what this means, the population regression function is missing this value by 50, and this is equal to ui. And if I take that out of which we have estimated 70, it means our regression function, that is here, it is missing this yi value by only 30. So this 30 is ui hat. So this is the story behind the regression, the introduction of the stochastic term, that we, as the line goes through only the population regression line, goes through the expectation, or you can say the conditional mean. So when there is mean, it cannot touch each and every value. Some values are above the regression line and some are below the regression line. So what we have to explain, that how much have been missed by mean. We can measure this. Mean is a rod here. So at every point we can see that how we have missed. And when we will be talking about this thing, we will be talking about the population regression function. But when we will estimate it on the sample regression, we will see that we have, out of this, we have abstract search information and information equal to that is unexplained. So here you can see that in case of sample function, 30, or you can say the 30% was the unexplained variation. So this is the same story. I think it will be enough helpful for you to understanding what is the value of introducing error term into the regression function. The problem of estimation. Now I would like to say that now we are going towards our true objective, that is the estimation of the parameters, that is the beta 1 and beta 2. And as you cannot estimate the parameters of the population, you will be doing it from the sample. Our objective is to estimate the population regression function on the basis of the sample regression function as accurately as possible. So there are many samples. The people come with different values of beta 1 and beta 2. We are interested only those values that are very, very near to the true parameter, that are the population parameter. There are many other methods, but two methods are very important. What is the OLS? I would like to write this, explain. This is OLS, ordinary least square. Ordinary least square, and this is the maximum likelihood method. Maximum likelihood method. These are used to estimate the intercept, that are the betas, intercept, and the slope coefficient. Now OLS is extensively used in regression analysis. What is the reason behind this? That it is much appealing and much simpler than maximum likelihood. But it cannot be said that the maximum likelihood is not useful. In some cases it is more, its significance is more powerful as compared to the ordinary least square method. But there are some of the commonalities between the OLS and the maximum likelihood. The first commonality is that the two methods generally give the same estimate of beta in simple as well as in multiple regression under the normality assumption of residual. So what this is, I am saying that if we take one assumption that our residual terms are normally distributed, I will say that what is normally distribution. If we say that the residuals are normally distributed, then the maximum likelihood parameter estimated from the beta 1 and beta 2 hat estimated from the maximum likelihood method or OLS method, they give the similar results in both the cases. So it means when we take the assumption of normality, we need not to worry about whether we are estimating our parameters by maximum likelihood or by the ordinary least square. And similarly in large sample. In small sample, this variance, this sigma square is variance. This sigma square is variance. Variance of the error term. So this variance of in a small sample it becomes biased. But OLS estimator, that this is the variance of OLS, this remains unbiased. But in the large sample, when the sample goes asymptotically large, then it becomes, this issue is also resolved. So before going to the next slide, what we learn from this slide? What this slide says that there are two common methods to estimate beta 1 hat and beta 2 hat. One is the maximum likelihood, the other is the ordinary least square method. Both methods are very important, and there are some commonalities. What are the commonalities? The first commonality is that both the method give the similar result in both the bivariate regression and the multiple regression when we take the assumption that the residuals are normally distributed. And there is another parameter, that is the sigma square, that is the variance. That is the variance. So sometimes means that in small sample, in case of maximum likelihood, it becomes biased, but in the large sample, again the variance of error term calculated from maximum likelihood or OLS, it becomes similar. Now OLS, in this our discussion and in this our course, we will just concentrate on the ordinary least square. We will be ignoring the maximum likelihood and we will be just concentrating on the ordinary least square. Who gave the method of ordinary least square? Thanks to a German mathematician, that was the Friedrich Gauss, who gave this method, and it is a very, very good method, and you will see that it has some charismatic properties and it helps us a lot in estimating this. For example, if this is you see that again I will be repeating the same thing, that this is the population regression function, it is not measurable, so we estimate this function, and if you see here, now this portion has become, that is the estimated, this is the explained, and this is the unexplained. So similarly we can write here that yi is equal to yi hat, that we estimated, and this is the unexplained. So if we are interested that how much we could not explain, we solve this equation for ui, and ui becomes ui hat. Now ui hat, that is unexplained variation, and it is equal to, this is the original value, and this is we have estimated. And if I give the ui hat and yi minus beta 1 hat minus beta 2 hat xi. So what this means, I have just replaced this yi hat by this one, because this is the explained or the estimated proportion, which shows that the ui residual are simply the difference between the actual and the estimated y values. What is our now purpose? There is some unexplained. I would like to take your intuition that whether we want that this unexplained proportion should be more and more or less, you will be immediately answering that this unexplained proportion should be very and very small. So I am coming here. So what is this? if I take the summation, I sum up this. So what this means, I want this should be as small as possible. Because if there is small unexplained, so yi hat will be converging towards the yi hat and there will be no difference. Now we have to see whether this thing is justifiable. As I said, that if we are interested in taking that the summation of yi minus yi hat should be minimum. Is it justifiable? If you remember and you are very smart, you will immediately come to know that the residual sum summation ui is equal to 0 from the previous example, and if we sum of all the residual, their sum becomes equal to 0. So what this means, when every time this term will be equal to 0, so what will be this purpose? Now how we will come to know if each and every time your solution comes equal to 0, so this is minimum. Then how we will decide that in this case it is minimum and in this case it is not minimum? I am going to explain this, and then we will be asking that we are not interested in minimizing the residual sum, but we are interested in minimizing some of the other term. I am going to explain this. If you look at here, this is again the regression line and this is the sample regression line. If you look at here, this is the ui hat. Ui hat means what is this? This is the yi hat. Y1 hat you can say. This is y1 hat and this is y1. So what this means, you estimated this proportion of this and this proportion was missed. And what this at this point, what this point is, was the y2 and you estimated this y2 here, that this is the y2 hat. So what is this here? This was the y3 value, that was the original or the actual value y3, and you missed it here and you estimated it y3 hat. And similarly the actual value, this was the y4 and you estimated it at this point y4 hat and you missed it by u4 hat. So what you are looking from is, if we are interested in this term, what we are doing, that we are just summing up u1 hat plus u2 hat plus u3 hat plus u4 hat. If you sum up all this, this will be equal to 0. For example, if this u1 I suppose that this is 6, this is plus 6, I suppose that this is minus 3 because it is below the line, and this is here you underestimated and here you overestimated. Here again I say that this u3, this is equal to plus 3 and this is equal to, again this is equal to minus 6. If I add up these, this will become 6 minus 3 plus 3 minus 6 and it is equal to 0. Here there are two problems. Two problems arises here. The first is that the residual sum is always equal to 0. So how we can decide? This is a very difficult and critical thing, that how we decide that this residual sum is a minimum. The second is, there is some injustice also in this regression line, that when we are adding up all the residual, these are u1, we suppose that there are 4 residual, we are giving the same weightage to each residual because just we are adding up these. This is not true, because although the residual sum is equal to 0, but some of the values you can see, for example, this yi and this y4, these are very away from your estimated regression line. So what this means, although the mean of the residual is equal to 0, but still it is not the true picture, because it is possible that some of the values are far away from the regression line, but the residual sum is again equal to 0. So what this means? It means it is hiding some of the information that is not telling us that although there is huge variation, huge, you can say, missing of the value estimation, then we are not we can't give the equal weightage to this one. So we go one step further, and what we say that no, we will give different weightage to each residual. Then we will see that now whether the sum of residual is less. For example, now we say that rather than expected value of ui hat, we are interested in the residual sum of square. We say in square what will happen? There will be two benefits of squaring this. The first benefit is a more relevant weight. We will be giving, when there will be squaring, for example, now 6 and 3, there is difference of only 3 digits. But if we will square, 6 will become 36 and 3 will become 9, and now there will be difference of 27. What this means, we have given the more weightage, the values that were away from the regression line. This is now true because we are penalizing the OLS, that why the regression through the estimated regression is not very near to the values. So in this way, it means we are testing the OLS, and this is a test time for the ordinary least square estimated to show us that now the residual sum of square is minimum. So what this means, we are giving more and more relevant to here, and the second benefit is that now the residual sum of square, not the residual sum, now we are squaring this. The first benefit is the equal weight gets the all different weights of all the residual or the missing value or the missing estimation gets. The other is that we are testing our OLS, we are penalizing the OLS, that if some value is away from it, we will give more weightage to it, and then we will show whether the OLS estimates are good or not. So the second is that we are interested is residual sum of square. So what this means, now rather than, now our target has become that we will be minimizing yi minus yi hat square. The sum of, this is the sum of, this is the summation of yi minus yi hat square should be minimum. In this way, that will give a better result for this. And interestingly, when there will be square, definitely there will be value, there will be no negative value, and every time there will be value something greater in case of square. In case of only the sum, every time there will be 0. We will, before deriving this, I would like to have some talk about its assumption. What are the assumptions of classical linear regression model? I will be explaining it in the next lecture, but here what I am saying, that why we take the assumption. Assumptions make us, enable us, all the social sciences theories are based on the assumption. So this estimation of the OLS that we will be solving in the next lecture mathematically, we see here that it is also based on some of the assumption. So what this means, we are talking about the assumption of classical linear regression model. So this will be classical linear regression model. So if I write, this is classical linear regression model. So we will take some of the assumption, and OLS estimation will be based on those assumptions. If we lap those assumptions, then we will come to know that there is some difference between the properties of the OLS. So this is, I think now it is time to wind up the lecture. And before going to the next lecture, I am going to tell you that in the next lecture we will be using some of the intense mathematics, that the concept that is the derivative, and I assure you that this will be the only derivation in the in this course. Because why this? There is huge and large and complex mathematics between each and every claim that we make here. But it will consume lot of time and lot of resources, and we have only 32 lectures to complete this. So our destination is very far away still from here, and we have to cover a lot of course. And by now I have been a bit slow, but you will see that over time I will be getting momentum and I will be getting some speed, so that we overcome and complete all this course. So now it's time to wind up the lecture and give you some brief summary of what we have covered today. We started from the population regression function. Now I will be just clear and very specific. Population regression function or the conditional expectation function are the similar things. Population regression function shows us that this is it is a regression line that connects that is the locus of the points that are the conditional mean of the independent variable against the fixed values of the independent variable, and this is the conditional mean of the dependent variable. Then we said that there are parameters beta 1 hat and beta 2 hat that cannot be estimated directly because we cannot study the population. So to estimate those, we indirectly used a method of that was the simple regression function. So in simple regression function, the terminology a bit changes, and we use the hat symbol over the estimated. So this was the beta 1 hat and beta 2 hat, and on the basis of this we can derive a sample. And as you know, there is another difference between the population regression function and the sample regression function. In population regression function, there are many values of the dependent variable as against the fixed values of the independent variable. But in the sample, we take only one value of against one fixed value of the independent variable. We take only one value and we choose it randomly, and we will be talking about what this is, the sampling, and we talked about rather that one. And every time when there are more sample, it means there are more regression line. And now there is the very interesting question arises that which line is the best. No rule of thumb, but we will be talking about the more nearer a sample regression line is to the population regression line, then it is called this is the best fit. So how we will come to know? We will be talking about this. We will be talking about the measurement error and standard errors of beta 1 hat and beta 2 hat. And then we will see that how we come to know that which is the best one or which is not the correct. Then we showed that what is the sample regression function and the population regression function, and it is still before me on the screen, and we showed this, that what is this. In problem of when we estimate the parameters, we use mostly the two methods. The first method is maximum likelihood, the other is the ordinary least square. Both methods have their advantages as well as disadvantages. But the one thing very interesting between these two methods is that they give the similar result under when we take some of the specific assumption. For example, under the normal distribution of the residual term, the disturbance term or the error term, the both method, maximum likelihood and the ordinary least square method, give the same values of the parameter, that is the beta 1 hat and beta 2 hat. And interestingly, it is true not only in the bivariate regression analysis, it is also true in the multiple regression analysis. In the next lecture, we will be deriving the OLS estimators, and we will be showing that how we come to know that the residual sum is equal to 0 or it is equal to and why we are interested in minimizing the residual sum of square. Only in 1 minute I am going to tell you that rather than minimizing the residual sum, we are interested in minimizing the residual sum of the square, because the residual sum of the sum of residual is always equal to 0. We have proved this, and that's why, and the other drawback of this is that the residual sum doesn't shows gives the equal value to all the residual. When we add up this, all the residual are tied with the same rope, and this is not true. The more values that are away from the regression line, they should be given more importance. That's why there will be test for the OLS estimator, and if the values that are very near to regression, that should be get least value. So that's why we went towards that there should be the minimum of the residual sum of the square. If OLS has the potential to minimize the residual sum of the square, then we will say that OLS is a good method, and if it is unable to do this, then we will be going some of the alternate, and we will be proving this mathematically under some of the basic assumption. So thank you very much. Allah Hafiz.